We're going to continue our discussion on the family of transfer functions, and we're going to again take the example of constant propagation. Last time we looked at a family of transfer functions which had three functions, but let's say I was interested in making my transfer functions more precise. And so this time, just like I had three different functions, so I had x colon equals c. In this case, out was just so the first transfer function that I use here, which is 1, which is fx equals, if x is top, then top, otherwise constant. The second transfer function we used was if x colon equals ex, then, I just say that, look, I mean, because ex can be non-constant, so I just use bottom for it. So if in is top, then out is top. If in is bottom, then out is bottom. So the second transfer function says that if x is top, then top, otherwise bottom. Okay, because x is being assigned some arbitrary value. Similarly, if I was assigning some value to another variable, an unrelated variable y, then the transfer function that I was using was the third transfer function, which was the identity function fx equals x. And finally, if I was assigning some arbitrary expression, so in this case the right hand side could be, let's say, y plus z. The difference between this case and this case is that here the right hand side is an expression on x, so for example x plus 1 or x plus 2. Here the right hand side could be an arbitrary expression that may involve other variables like y, z, etc. And so in this case also I'm using the second transfer function, which is if x is top, then use top, otherwise use bottom. So this is the family of transfer functions that we looked at in our last lecture module. But let's say I was interested in making this family of transfer functions more precise. In particular, I'm interested in looking at this this instruction, which is basically doing x colon equals ex. And for example, if I know that in is giving me a constant value for x, for example, if in was saying that x is 3 and this ex was an expression on x is just x plus 1, then I can say that the out should be 3 plus 1, which is 4. But our current transfer function is too imprecise and just lowers it down all the way to bottom. But we could have done better, and let's try to do it better and then again check whether the new transfer functions actually satisfy our requirements for them to be a DFA family of transfer functions. Okay, so let's say I use this more precise transfer function for this particular case, and in this case I'm using the transfer function called the fourth transfer function, number 4. And this is what number 4 would look like. If x is top, so if in is top, then out is also top. If x is bottom, then out is also bottom. But if x is some constant c, then the out is e evaluated on that constant c. So for example, if e was x plus 1, then e of c would be c plus 1. And so this is a more precise transfer function. And the question is, does this set of 4 transfer functions also satisfy the rules for it to be a DFA family of transfer functions? So to answer this question, I need to first say, like, what are all the possible e's that I will support? For example, will I support arbitrarily complicated expressions like, or am I going to do something different? So let me, for argument's sake, say that I'm only going to support that case where ex was a simple expression x plus 1. And I'm not going to support anything else. For example, I'm not going to support 2 into x, or I'm not going to support x plus 2 or things like that. Only if ex is x plus 1 am I going to change c to c plus 1. All other cases I'm just going to change c to bottom, right? Just like I was doing earlier. So in this case, what it means is that if this statement was x colon equals x plus 1, then indeed I'm going to do fc equals c plus 1. But if it was some other statement which was not amenable to the transfer function of x plus 1, for example, x colon equals x plus 2, then the transfer function fc would just be bottom, even if the input value is coming in is a constant c. So if I use this, this is a valid set of functions, but the question is it a valid DFA family of functions? So once again, I need to check all my 3 rules. And the first 2 rules are actually still satisfied because, after all, we are still mapping a domain of values to a domain of values. The fourth function is also mapping domain of values to domain of values. The last case is actually never going to happen, so we don't need to worry about it. Because, either input is going to be top or bottom or C. So the last case is never going to happen. And the outputs are also either top, bottom or C. So it does follow this first rule. Also follows the second rule because the ID function is still available in my family of functions. It's the third function. But the third rule, which involved checking whether the composition of two transfer functions also yields a function in the family of functions. So if I, for example, compose 4 with itself, then I get something like this. If I simplify it further, and I basically get something like this, I get E composed with itself. So E composed with itself, or E2, E square applied on C. Now, if the only function that I'm allowing for E is x plus 1, then E square would become x plus 2. And that actually is not, so actually this should have been not C, but x. So now that function will become x plus 2, but x plus 2 is no longer present in my family of transfer functions. So this becomes C plus 2, sure, and this does not belong to F. This does not belong to F because this function 4 composed with 4 yields a function that's not equivalent to any of the 4 functions that I have in my family because of the presence of C plus 2 here, but C plus 1 here. Now, so here EC is, I'm assuming that EC can only take the value C plus 1 and that's it. So this is not a valid family of transfer functions. I just wanted to give you an example of a family of transfer functions or set of transfer functions which does not satisfy those 3 rules. So how does it matter? I mean, how does it matter if this set of functions does not satisfy the 3 rules? Well, because compositions are no longer present in my family of transfer functions, it creates all kinds of weird situations. For example, let's say my original program was, a sequence of 2 assignments, x colon equals x plus 1 followed by x colon equals x plus 1. If I apply my transfer functions, then I use the best possible transfer functions, then across 0 and 1 program points, I would get, let's say initially the input value was 0, then across this first instruction, I will get C plus 1, which is 0 plus 1, which I'll get the value 1 for x. And then once again, I apply the second instruction and I'll get 1 plus 1, which is again 2. And this is all this is permitted by my family of transfer functions because it includes this special handling for x plus 1. But let's say, the DFA analysis kind of wanted to treat both these instructions as a single instruction. For example, if they were in the same basic block, they want to define the transfer function of an entire basic block. And so it wanted to change this x colon equals x plus 1 and another x colon equals x plus 1 to x colon equals x plus 2. In which case now, the transfer function across this entire compound instruction is not, we don't have x plus 2 in our set of family of transfer functions. And so the only possible transfer functions that can work across this compound instruction is the one that assigns bottom to the output value. And so this is not a very happy situation because just because I decided to use certain group the instruction in a certain way, the answers that I'm getting are very different, and there's no way I can get the same answer that I was getting earlier. So, and that's for the reason why we want that the composition of 2 functions should also be present in the family of transfer functions. And here's an example here's an example of functions where E is restricted to x plus 1, that's not true, and which can cause all these kinds of instabilities in our data flow analysis. However, if I just change my E to support not just x plus 1, but x plus any constant k, where k could be any constant greater than or equal to 0 in the set of integers values that x can potentially take, then 4 composed with 4 still belongs to F, because if you compose 4 with 4, and let's say the first 4 had the value k1 for C plus k1, and the second one had k2, then k1 plus k2 is still greater than or equal to 0, and so you're still okay. So it's always these mathematical properties actually help us make the problem more structured and easier to tackle, so that we can have better properties and stricter properties on them, so that we can have stricter properties on our data flow analysis.